Hi everyone, today I will present to you our paper on the sensory commutativity of action sequences for embodied agents. It's a joint work with Michael Garcia-Ortiz and David Filia, which are both my PhD supervisors. In our paper we focus on the embodied agent scenario. So in this scenario we have an agent in an environment, and the agent is able to perceive the environment through its internal sensors like eyes, and it can act on the environment using its motors, basically like a robot, so joints with articulated arms and head-based movement. And in our paper we introduce the sensory commutativity of action sequences. So we first start from the commutativity of action sequences. You can have action sequences that if you change the order of the sequence, you still have the same sequence. And moving from that, you can define the sensory commutativity of action sequences as being, so let's say we start in a starting situation and we plan action sequences in two different orders. We can say that they sensory commute if the end sensors observed after these two different orders is the same. So basically the action sequences are equivalent in terms of sensors from this starting situation. So here's a quick example of how two action sequences can not commute. So if we start from this common starting situation here, and we do the first action sequence, which is go left and go left, and then the second action sequence, which is go right and go right, you can see that we didn't move the mug. But if we play the action sequences in different orders, so we start with go right, and then we do go left, we can see that the mug has moved, and so the two action sequences from the same starting situation do not sensory commute because the sensors we observe at the end is not the same. From that, we can define the sensory commutativity probability, which is basically the number of times action sequences do commute when we average with the number of starting situation and also the different action sequences that you can create. So we can define this criterion for each degree of freedom of the agent, and we will see after that that it kind of quantifies how much this degree of freedom can act with the environment or not. So basically what we obtain is a hierarchy of the degrees of freedom when we compute the sensory commutativity probability for the agent. So as you can see here, if we compare elbow joints to shoulder joints move things around a lot more than elbow joints, and so they are more likely to hit objects and stuff, and so if we compute the SCP, it's more likely that the action sequences played in different order do not commute. And that's what we obtain here. You can see that the SCP is much lower for shoulder joints than for elbow joints. That's because shoulders are more likely to hit objects. And so basically when we compute the SCP for all of the degrees of freedom, we have this hierarchy among the degrees of freedom that can basically tell you if your degree of freedom is useful for navigating, manipulating stuff, or if it's just useful for perceiving the environment, like head rotation or eyelid activation. And a nice thing about the SCP is that it scales to complex 3D robotics environment as well. So the first example was a 2D simulation. Here we work with a 3D robotics simulation called iGibson Simulator. The robot here is the fetch robot with 2 wheels and long articulated arms with 7 joints, and it can also move its torso up and down. And so it is placed in an apartment, and it perceives the environment through its camera here. And when we computed the SCP of this robot in this environment, we had the same type of hierarchy, where we first have the wheels that have a very low sensory commutativity because they interact with the environment a lot. And then the SCP grows higher and higher for arm joints that are farther and farther from the center of the robot. that's the same type of concept as with shoulders and elbows. Basically, the joints that are closer to the body allow you to move the arm a lot more than arm joints that are farther from the body. We also did experiment where we showed that SPP can be useful for reinforcement learning. So thank you very much for watching. I hope to see you all online during the workshop. And if you want to contact me, you have my mail, GitHub, Twitter, and website here. Don't hesitate.